Hello students, good afternoon everyone. This is Ramsoro, Maths faculty. I welcome you all to Turito live classes. Children, today we are going to discuss about a continuation of the yesterday's class, like previous class children. In the previous class children, we have discussed about, do you remember children anything? So what was the previous class? Yes. Children, the previous class we have discussed about what? Introduction of HCF. Okay. And then we have discussed about the relationship between the what? LCM and HCF. And few problems we have discussed related to what? How to find the LCM. Okay. How to find the LCM and how to find the HCF. And the relationship between the what? LCM and HCF. Isn't it children? Yes. Children, can you please tell me what is the relationship between the LCM and HCF? Do you remember anything like previous class? Suppose A comma B are two numbers children. So A is a one number and B is a both are what? A positive numbers. Okay, we can take something a positive integers. If A comma B is the integer, then I am writing HCF is what? HCF of A comma B. Then I am writing LCM is equal to what children? LCM of A comma B. Okay. So I want to write the relationship between the what? HCF and LCM. Tell me children how we can write? I told you a shortcut also. Okay, listen here. So we can write as HCF of A comma B into LCM of A comma B. So we can write as what children? A into B. So children, it is a relationship between the what? LCM and HCF. Shortly you can remember as LH is equal to P. Here L indicates what? LCM and H indicates what? HCF and P nothing but product. So product of both the numbers. Okay. So that is a relationship between the LCM, HCM and their product. Clear children? So this is actually about the previous class. Okay. So that is called a recap. Fine. And children, today's session. Okay. So we are talking about, otherwise we are discussing about introduction of rational numbers. Okay. So we are discussing about what is a rational number and what is the properties of rational number and which numbers we can call them into a rational number. Okay. That is about introduction of rational number. And next one, a decimal expansion. Okay. Then the types of decimal expansion. So decimal expansion and how many types we have the decimal expansion. Okay. So this is about the today's class children. So I can say it is the agenda of today's class. Like we can say learning objectives. Okay. Now children, let us start this class. First we will start the what is the real number? Real number, rational number. It is a real rational number, sorry. So we are going to talk about what? The rational number introduction. What is the rational number and what are the types of rational numbers? Do we have any types of rational numbers or we have only one type? Children, we have the only one type rational number. Okay, we don't have any types of rational number, but we have the different kinds of identifying the rational numbers. Like which numbers we can call them into rational numbers. So that is a different types of examples. Now children, rational number. Can anyone please tell me what is a rational number, children? How we can define a rational number? So what are the numbers we can call them into rational number? Children, this is a definition I already discussed in the first class. So introduction of real numbers. So there I have discussed everything. So what is the natural number, whole number, integer, rational and irrational. So there I have covered everything, these children. Now tell me what is the rational number here? How we can say, like, what is the definition of the rational number? Children, I told you already, rational means what? We can think as it is a ratio. Yes or no? Rational number means it is a ratio form. So ratio nothing but what, children? A numerator by and it is a denominator. So these type of numbers we can call what? A rational number. Isn't it? You can take one example, 4 upon 3. You can take minus 9 by 5. Isn't it? You can take something 13. Wait a minute, children. You can take something 19 upon 23. Isn't it? These are all what the examples of the rational number because they are in ratio form. Okay, the number is in the form of ratio form, so we can call it as a rational number, isn't it? So it is a rational form, 4 by 3, so 4 upon 3, minus 9 upon 5, it is a rational form, 19 by 23, it is a rational form. Okay, so these all numbers we can call what, children? These are rational numbers. Rational number means it is a ratio form, simply. Rational means ratio. Okay, now children, let us see the definition of rational number now. A rational number that is in the form of what, children? P by Q form. Okay, so the rational number means it is in the form of a P by Q form. Clear, children? And here what is the P? It's a numerator and Q is a what? Denominator. Clear? But my question is, can I take any value of P and can I take any value of Q and can I substitute there? Is it possible, children? Or do we have any condition for selection of what? P value and Q value? Or simply we can take any value? So without any like having the intention? Tell me, children, do we have any criteria or do we have any terms or condition for selection of P and Q value? Yes, children, we have some terms and condition. You think as it is something condition, it is not a terms. So P should be what, children? Integer. And Q should be also integer. So P should be integer and Q should be integer. But what is the one more condition for the Q? A Q should be a non-zero integer. That means Q should not be equal to 0. Q should be what? A non-zero integer, children. You can substitute P as 0, not an issue. You can take P as a 0. But you cannot take Q as a 0. Are you getting my point, children? If you take suppose 4 upon 0, I am taking Q is equal to what? 0 number. Okay. So can you define, children, this value? What is a 4 upon 0? Is it possible to define? So 4 by 0 gives what, children? It is undefined form. Are you getting my point? So to overcome this kind of problem, so we have taken one condition for the Q. Here Q nothing but what? Here denominator. So Q should not be equal to 0. So this condition we are applying whenever we are writing any rational number. Am I clear, children, this point, everyone? It is so simple, children. Rational number nothing but is a ratio form. So ratio nothing but what? P by Q form. So here P and Q both are what? Integers. P also integer and Q also integer. So P you can take any value, but Q you cannot take 0 number, children. Q should be a non-zero integer. That means Q you can select any value except 0. You cannot take Q as 0, children. Okay. So that is the condition for what? Selection of a Q value. So apart from everything is common only. Like P you can take integer and Q also you can take any integer. Okay. So that is the definition, children. The number should be in the form of what? P by Q, and P and Q both are what here? Integers, and Q is what? A not equal to 0. Okay. And the rational number denoted by is what? The English letter is what? A capital Q. Okay, here Q nothing but quotient here. So when you divide the both number, then only you will get the quotient, isn't it? If you do the addition, if you do the subtraction, if you do multiplication, you will get the quotient. No. When you do the division of any two numbers, you think it is a one number and you think it is a one more number. So you're doing the division of these two numbers. So what you will get here generally? Quotient only. Okay. So here quotient nothing but Q. So we can write, like we can represent all the rational number. The English capital letter is Q. Clear, children, this point, everyone? Okay. Now, children, this is actually a rational number form. So P and Q, like P by Q form. Okay. So P is the what here? Some integer, and Q also integer. But which integer I am selection, children? It is a non-zero integer. So Q I can write, children, Q equal to, so this is what? A P by Q form, isn't it? Rational number means what? It is a P by Q form. And what is P and Q here? That I am writing the condition. So P Q is belongs to Z, and Q is what? A not equal to 0. Are you getting my point, children? P and Q both are what here? Integers, and Q is what here? Not equal to 0. So in that case, then only we can say it is a real rational number, not real number. See, rational number also real number only. Okay. But all the real numbers are not rational numbers. But I can say all the rational numbers are real number. But real number is what? Is a combination of what, children? So R is nothing but what? Q and Q bar. I can say all the rationals are reals, but I cannot say all the reals are rationals, isn't it? Because real concludes what? Includes irrationals also. So irrational cannot be called as rational. That is not possible. So what I can say? I can say all the rationals are real numbers, but I cannot say all the reals are rationals. Is it clear, children, that condition? Okay, fine. Now, children, rational number example. Let us see one by one. So, what are the numbers we can call generally rational numbers? First example, can I say it is a rational number, children? Yes, 1 upon 2. Yes, it is a rational number. So, I can say it is a rational. Next example, children. Minus 3 upon 4. Can I say it is a rational number? Yes, it is also rational. Next example, 0.3. Children, this 0.3 I can write as 3 upon 10 also. So 3 upon 10 means what? Can I say again it is P by Q form, isn't it? So it is what? A P by Q form. So P by Q form nothing but again I can say it is a rational number, isn't it? So 0.3 also we can write as 3 by 10, like 3 upon 10. Again 3 upon 10 is a form of what? It's a P by Q form. So I can say it is a rational number. Okay. So I can say it is a Q. Next one, minus 0.7. And same thing, children, this minus 0.7 also again I can write as minus 7 upon 10. So this minus 7 upon 10, what we can say, children, again it is a what? A rational number, isn't it? Okay, because again it is formed in the rational form, that is P by Q form. So P by Q form nothing but again we can say again same rational number. Okay, so children, these are the types of what? Examples of rational number. And children, this type of numbers. So these are the what? A special type of decimal expansion, children. So that we will discuss slowly one by one. But now remember, this also what? A rational number. So this expansion we can write as 14 by 99. So 14 by 99 is what? Is a rational number. Children, we can say like what are the decimal expansion are rational numbers, and what are the which decimal expansion not in the rational numbers, that we will discuss slowly now. But as of now you can remember this 0.141414, we can say 14 by 99, and 14 by 99 is a what? Is a rational number, because it is in the form of what? A P by Q form. Clear, children, up to here? Are any doubts? So what are the types of examples of rational number? Which numbers we can call them examples of the rational number? It's a very simple, children. Okay. Next, types of rational numbers. Again same, which numbers we can call rational numbers? Children, you can take all the integers. Okay, you can take all the integer like positive integer, negative integer. See, I can say 4 is a rational number. But you might be saying like 4 is not in the form of P by Q, isn't it? But children, 4 we can write as 4 upon 1, isn't it? 4 by 1, both are same only, isn't it? So I can say 4 or 4 by 1. So both are what? A rational number. So 4 I can write as 4 upon 1, and this 4 upon 1 we can say it is a P by Q form. If the number is in a P by Q form, means we can say directly it is a rational number. Okay. So I can say all the integers I can conclude as a rational numbers. Okay. That is the first type of example. Next one, fractions. Some fractions will be there, children, like minus 3 upon 4, like 6 by not 3, children. We can take something. We can take something 6 by 9. Any fraction, if it is in the form of P by Q, and where Q is equal to not equal to 0 form, so that is called what, children? Is a rational number. So any fraction means what? Something by something here. Okay, a fraction which has numerator and denominator are integer, so we can call them into what? A rational number. Okay. any fraction which has numerator and denominator are integers where q is equal to not equal to 0. So those type of we can call examples of a rational number. Next one, terminating decimals. Like children, these type of numbers we can call what decimal only, but in the decimal we can say terminating decimal expansions. The next time, like in the next slide, I will going to discuss what is terminating decimal expansion, what is non-terminating. Okay, that we will discuss now. But children, you remember these type of examples. Also, we can take as the example for what a rational number. So 0.35. So this 0.35, how we can write, children? Listen here. So this 0.35 I can write as 35 by 100. So when you cancel again, this is what 5 7s are, and this is what a 5 20 times. So this I can write as 7 by 20. So this 7 by 20 is what, children? It is again in the form of p by q. So it is a form of what, a p by q. So I can say it is a rational number. Children, remember blindly, if any number, if it is in the form of p by q, otherwise you can able to write in the form of p by q. So that is what a rational number. If you are not able to write in the p by q form, so it is called irrational. If you are able to write, it is p by q. So it is called what, rational. If you are not able to write in the form of p by q, it is an irrational number. Okay. So I can say this number is what, a p by q form, like 7 upon 20. 7 is a p value and 20 is a q value. So I can say this number is what, a rational number. Okay. And so now let us see next example. Non-terminating and repeating decimal expansion. Non-terminating repeating means, children, non-terminating means you will get the digits continuously. Repeating means what, children? Same number repeatings. Like here 6 is repeating. Otherwise you can take 0.33333. So here 3 is repeating. You can take 0.454545 and so on. Okay. So children, these type of decimals are called what? Non-terminating repeating decimal expansion. So all non-terminating repeating decimal expansion we can call into what, children? Examples of rational number. These are all called rational because we can write in the form of p by q. It is possible to write, isn't it? So I can say these are called what, children? Rational numbers, a non-terminating repeating decimal expansions. Okay. So these also we can call to, otherwise we can take as what, examples of rational number. Clear, children? Any doubts regarding the different types of rational numbers? First one is what, integers. Next one is like fraction with a numerator and denominator, where numerator and denominator are what, integers. And second one is what, a terminating decimal. Okay, like termination 0.35, it is an example for terminating decimal expansion, and you can write as 0.7116. This also what, children? A terminating decimal expansion. And next one is, last one is what, a non-terminating repeating decimal expansions. Like the numbers are like this form. Okay, this is what, a non-terminating and repeating, because here 6 is repeating continuously. So these are called what, children? These are a non-terminating repeating decimal expansion. So this also we can say the good example for a rational number. Clear, children? Any doubts regarding this all examples, different kinds of examples? Okay, fine. Next, how to identify the rational number. Okay, so children, that's also very important. See how we can identify. First one, if we can represent the given number as a fraction of integer. I told you already. If any number you are able to write in the form of p by q, where p and q both are integers and q is not equal to 0. So blindly you can say that number is what? Rational number. Okay, that is the first point. And second point is what? When the decimal expansion number is what? A terminating or non-terminating repeating. Decimal expansion should be what? Terminating or non-terminating repeating. So then also we can say that number is what? Example for. Otherwise we can say that number is what? A rational number. It should be terminating form, or it should be what? A non-terminating repeating decimal expansion. Clear children this point or any doubts? Okay. Next, types of decimal expansions. Tell me children, how many types we have generally? Decimal numbers. Any idea? Terminating, non-terminating, repeating, non-repeating. Did you listen this children? Did you heard this type of like words? Terminating. So what is the meaning of terminating children? Okay, let us see first how many types we have the decimal expansions. So generally children we have the exactly 3 types of decimal expansions. First one is what? A terminating. It's a very simple. Okay. And next example is what? Non-terminating but repeating. Generally exactly we have 2 types only. One is terminating and non-terminating. But in the non-terminating again we have 2 types. One is terminating, one more is what? A non-terminating, isn't it? So this is what? A non-terminating repeating. Next one is what? Non-terminating, non-repeating. Okay. So these are the what? A types of decimal numbers. We can say types of decimals. First one is terminating. Second one is what? A non-terminating repeating. Next one is what children? A non-terminating non-repeating. Okay. So these are the what? A types of the decimal numbers. Clear children? Any doubt? Types of decimal expansions. First one terminating and second one is what? A non-terminating repeating and next one non-terminating non-repeating. Okay. Now children, let us see one by one. What is this terminating? What is this non-terminating? And what is this non-terminating and non-repeating? Now children, let us see first one. So what is the terminating decimal expansion children? Any idea? First tell me what is the meaning of terminating? Termination. Terminating. So what is general meaning? Like English meaning, not like mathematical. I am asking general meaning. Okay. English. Termination means what? Stopping. Isn't it? People terminate their service. That means what children? They are stopping his service. Terminating means generally it is a stopping. So what we can say here? Terminating decimals. So stopping here. Stopping means what? What we stop actually. Okay, let us see what we are stopping here. Terminating decimals are those decimals that have the finite number of digits. Okay, I'll tell you. So I am writing 0.345. Children, after 0, I wrote the decimal point, then I wrote the 3 numbers 3, 4, 5. So after 3, 4, 5, I stopped writing. Are you getting my point, children? I am not writing continuously digits. After 0.3, then I wrote, so after 0 point, I wrote directly 3, 4, 5. Otherwise, I can write after 0 point, I can say 7, 8, 6. So after 0 point, I wrote 7, 8, 6, then I stopped. Isn't it? So this is called what? A terminating decimal expansion. Because I am not writing here continuously for a long time. After 1 or 2 digits, like after 3 or 4 digits, I am stopping writing. So this type of we can call children terminating. Terminating decimal expansion. Okay. This type of decimals we can say a terminating decimal expansions. Clear children? Any doubts regarding this? Terminating decimal expansion means what? The terminating of decimals are those decimal numbers that have the finite number of digits. See here. After a decimal point, I have exactly 3 digits. If I am writing some more example, 0.2645. So after decimal points, how many numbers I have? Exactly something 5 numbers. So the decimal should be counted, like the decimal numbers, like this also what they are all decimal digits. It should be counted, children. It shouldn't be uncountable. It should be counted. When the digits are finite, and when the digits are what? Countable, then we can say it is a terminating decimal expansion. Clear children my point everyone? It is very easy children. The number of digits are finite. The number of digits are countable. Then that expansion we can say a terminating decimal expansion. That's it. Very simple. Okay. Let us see children definition. That means the number of comes after a decimal point certain number of repetition. Okay. So that is a decimal expansion. You can see example children. See, I can say it is terminating decimal. 0.5. After 5, I am not getting any digits. Like after 5, the what is called the expansion is stopped. The expansion is what? Terminated. Okay, so we can say it is 0.5. You can take 0.678. After 3 digits, expansion stopped. 14 points. See 1, 2, 3, 4, 4, 5. After how many digits, children, here? 1, 2, 3, 4, 5, 6. After 6 digits, the expansion is terminated. 1.23. After 2 digits, expansion got terminated. 0.00024. After how many digits, children? 5 digits. After 5 digits, the expansion got terminated. Okay. So these are the what examples of what, children? The terminating decimal expansion. Okay. Next one. What is the non-terminating again? Non-terminating what? After decimal point, you will be getting the digits continuously, infinitely digits. There is no countable. I can say the number of digits are what here? Uncountable. You cannot say what is the number of digits exactly to me. Can you say, children? See, I am writing something here. Can you tell me, children, how many 3 6 are there here? Tell me. How many 3 6 are there? Like 3 6, 3 6, 3 6. Like this, how many are there in this expansion? Can you tell me exactly? You cannot. Okay. So we cannot say here number of like 3 6 are how many? Because it is what? A non-terminating. So this expansion is non-terminating. Okay, because we are getting the digits are continuously, we can say endlessly. In that case, we cannot say what is the number of digits. I cannot say what is the count of these digits. Isn't it, children? So in that case, I cannot say what is the count. The count is impossible to say. So that is the way I can say a non-terminating decimal expansion. Okay, children? Let us see the definition. A non-terminating decimal are those decimal numbers that have infinite number of digits. Are you getting my point, children? They have infinite number of digits. The count is what? Uncountable. Are you getting? The count is uncountable. So the number of digits are what? Infinite. Here the number of does not come to end. The number is what? It's not going to be end. So that is called what, children? Non-terminating decimal expansions. Children, look at here example 1.3333 so on. Can you say, children, it is? What is the example for this? It is a non-terminating because we don't know how many 3s are repeating here. Can you tell me? Count? No, we can't. And what about here? 52.36363636 and so on. So this also I can say what? A non-terminating decimal expansion. We don't know what is the count of 3 6. And what about this, children? Again same. We don't know how many digits are coming, like where the digits are ending. So that count also we cannot give. And what about this? Again same manner. The count I cannot give. We are getting what? Endlessly digits, uncountable digits. In that case, how can you say the number of digits are finite? No, they are not finite. They are infinite. Infinite means what, children? They are non-terminating decimal expansions. That's it. See, children, any doubts regarding this definition and regarding this example? No? Okay, then that's great. Now, children, another type. In the non-terminating, I told you. In the non-terminating, I have exactly two types. One is what? Repeating. One more is what, children? A non-repeating. So we have the two types, that is called repeating, and one more is what? Non-repeating. So that is called what? Non-terminating repeating, and it is what? Non-terminating non-repeating. Okay. So non-terminating repeating are called what? Rational numbers. So those numbers we can write in the form of P by Q. But these numbers I cannot write in the form of P by Q. Are you getting my point, children? That is why these numbers are called what? A non-terminating, non-repeating numbers are always irrationals. that is q bar. Okay, children. Now, children, let us see what is exactly non-terminating repeating and what is non-terminating non-repeating in detail. Okay. Now, first one, repeating decimals, non-terminating repeating. Okay. Now, repeating decimals are those numbers which a specific number repeats uniformly after the decimal point. Are you getting definition, children? Repeating decimals are those number, a specific number. Okay, number or numbers. It may be a single number, it may be plural number like 2 digits also. It not compulsory one number, children. It may be 2 digits like 2 numbers, or it may be 3 numbers also sometime. Okay, they should repeat, children. They should repeat what? Uniformly, continuously. Okay, so such numbers we can call the what we call repeating decimal expansion. I'll give an example. 0.999999 so on. Children, see, first of all, it is non-terminating because we don't know how many 9s are there, isn't it? So it is non-terminating. Now, can I say it is repeating? Yes, it is repeating because here the digits 9 is repeating continuously. Yes or no, children? Here 9 is what? Repeating continuously. So in that case, this number is called what? Non-terminating. What we call repeating. This is called what? A non-terminating repeating decimal expansion. Children, let us see some examples. See, 0.55555. I can say it is what? A non-terminating repeating decimal expansion. Next one, 13.26262626. So this also I can say example for a non-terminating repeating decimal expansion. Next, 1 point what? 87. What is the repeating, children, here? Here repeating is what? 8769. Here also 8769 will come something. Okay. So here how many digits are repeating? Here 1 digit repeating. Here 2 digits repeating. Here total how many digits are repeating? 4 digits are repeating. Digits may be anything. It may be 1 or 2 or 3 or 4 anything. But the same digit should occur immediately. Like after 5 immediately again 5. After 26 again immediately 26. Like after 8769 again after 8769 will come. So those we can call what, children? A non-terminating and repeating decimal expansions. See, children, any doubts regarding this definition and examples? See, children, definition is simple. Okay, fine. Next one is what? Non-repeating decimals. So what is a non-repeating decimal, children? Non-terminating, non-repeating. Terminatings are two types, repeating and non-repeating. So repeating we have discussed. Now we are discussing about what? A non-repeating. Okay. Now what is a non-repeating? Listen here. A non-repeating decimal, there is no uniform repetition. Okay. So none of the digits are repeating there. All the different digits are what? All the different digits. Okay. Like example, 0.3678 something. So it is called what, children? Non-terminating, non-repeating decimal expansion. Okay. So this is, we can say, a non-terminating and non-repeating decimal expansions. Here none of the digits will be repeat, children. No repetitions here. All the digits are different. So in that case we can say this is called what? A non-terminating and non-repeating decimal expansion. Children, look at here example. So I can say this also what? A non-terminating repeating. This also a non-terminating non-repeating, non-terminating non-repeating, and this also what? A non-terminating non-repeating. So all the examples, just look at there. First of all, it is non-terminating and it is a non-repeating because all the digits are different here. So in that case, what we can say, children, these are what? A non-terminating and non-repeating decimal expansions. Clear, children, this point? Are any doubts? Okay. Now, children, let us see what is the decimal number chart shortly. First of all, decimal expansions of rational numbers. So decimal expansion. So total how many types we have decimal expansion? 2 types. First one is what? A terminating, and next one is what? Non-terminating. For terminating, no need to worry. You can get the direct answer. Okay, no need to talk about the terminating. They are very good friends. But we have the problem with only these fellows. This non-terminating. So this non-terminating is a danger fellow. He is a good fellow. He is a danger fellow. Okay. So good fellow, he won't do any harm. But we have to manage the bad fellow. So managing the bad fellow is what? We need some extra skills. Okay. So let us see what is the extra skills. So in that we have the repeating and we have in non-repeating. Okay. So repeating rational number and non-repeating rational number. Clear, children? Fine. Next one. Children, we have one theorem. Let us see what is actually the theorem. Let x be a rational number, children. Okay. I am taking some decimal expansion. I am taking what? A 0.37. It is a decimal number and it is what? Terminates. Okay. X is a one rational number and it is what? A terminates. Terminating means what? After decimal point you will get the exactly fixed number of points. And x can be represented as in the form of p by q. Decimal number means what? It is a rational number and it is terminates. So if it is terminates means that it can be expressed in the form of what? P by q, where p and q are what? Co-primes, and the denominator q will be written in the form of 2 to the power of n and 5 to the power of m. Children, listen, is very simple, I tell you. Suppose you have any decimal number. Which number decimal number? A terminating decimal number. So I am taking a 0.45. So I am taking one what? A 0.45. So this is what? A terminating decimal expansion. If this is a terminating decimal expansion means you can write in the form of p by q. So it is what? A terminating decimal expansion means you can write in the form of p by q. If you are writing in the form of p by q means the denominator always in the form of 2 to the power of n and tell me, children, 2 to the power of n and 5 to the power of m form. So that is the condition. First, terminating decimal expansion. So we can write in the form of p by q. If you are writing form of p by q means denominator can be write as 2 to the power of n form and 5 to the power of m form, and n and m both are what? A positive integers. So that is the theorem. Terminating decimal expansion. So we can write p by q form. If you are writing something p by q form means what, children? Denominator can be in the form of 2 to the power of n and 5 to the power of m form. Okay. So 2 to the power of n and 5 to the power of m form means m and m are positive integers. Clear, children? Are any doubts regarding this step? Okay, I'll take one example. I'm taking something 0.36. So can I say it's terminating decimal expansion? Yes. So terminating decimal expansion means I can write in the form of p by q. So how we can write in the p by q? We can write as 36 by 100. Okay. And this 36 by 100 again I can write as, children, how we can write 100? Shall I write 2 square and 5 square, children? Yes or no? 2 square value 4 and 5 square value what? 25. So 25 into 4. So I can say it is 100. So this I can write as 36 by 2 square and 5 square, and denominator is in the form of what, children? 2 to the power of m and 5 to the power of m form. Clear? So that is a theorem. If a terminating decimal expansion, we can write as always in the form of p by q. After writing the p by q form, the denominator q can be written in the form of 2 to the power of n and 5 to the power of pm form. If this is possible means this figure also possible. That's it. Clear, children, this theorem? Are any doubts? Okay. Next, we can take example 3 upon 8. Children, can I say first one, you do one thing. Just take the denominator. What's the denominator here? 8. So 8 I can write as 2 to the power of 3 and 5 to the power of 0. So 2 to the power of 3, 5 to the power of 0 means, can I say it is a terminal decimal, sorry, expansion is terminating? Yes or no? This expansion is what here terminating? Because denominator I am writing as what, 2 to the power of n and 5 to the power of m form. So I can say it is terminating decimal expansion. Next one, 13 by 125. So how we can write 125 children? I can write as 2 to the power of 0 and 5 to the power of 3. 5 to the power of 3 means what? 5 into 5 into 5. So 5 5 is a 25, 25 5 is a 125. Okay. So that is also possible. Again I can say it is terminating decimal expansion. And children, you can try these 2 examples, this 7 by 80 and 145 by 88. Okay, so you will be getting the denominator as in the form of what children? 2 to the power of n and 5 to the power of m form. Okay, fine. Next theorem children, if any number p by q form, okay, suppose I have one rational number, it is in the p by q form. Think that the denominator, if you are not writing in the form of what, a 2 to the power of n and 5 to the power of m form, you are not able to write. Think that denominator you cannot write in the form of this 2 to the power of n form and 5 to the power of m form. Then what we can say, that is decimal expansion. The decimal expansion will be what children? A non-terminating and repeating decimal expansion. I will give an example children. I have one ratio, like a rational number is 4 upon 9. Here 9 I can write as children 3 to the power of 2. But this is not equal to what? A 2 to the power of n and 5 to the power of m form. Isn't it? So in that case, what I can conclude about this 4 by 9? It is terminating and non-repeating. Yes or no? Because here denominator is not in the form of 2 to the power of n and 5 to the power of m. If it is not in that form, then I can say it is non-terminating and non-repeating decimal expansion. If it is only like 2 to the power of n and 5 to the power of m form, then I can say it is terminating decimal expansion. But here 3 square is what? It is not equal to 2 power n and 5 to the power of m form. So what is my conclusion? It is a non-terminating and non-terminating and repeating decimal expansion. Next children, so what are actually summary of this class? In this class we have discussed about rational number. Okay. Next we have discussed what? A decimal expansion. I told you already how many types we have decimal expansion. Exactly we have 3 types. First one is terminating. Second one is what? Non-terminating repeating. And third one non-terminating non-repeating. See, these are the what? Types of decimal expansion. Next children, let us see 1 or 2 examples. Then we finish the class. See children, without actually performing the long division, whether we have to decide this expansion is what? Terminating or non-terminating. Okay. I don't want to do any normal division. By looking at the question, I wanted to decide whether it is what? Terminating or it is non-terminating. Are you getting my point children? See. First I am taking one denominator. Just look at the denominator. What is the denominator here? 3, 1, 2, 5. So children, I will go for directly which table? 5 table. 5 how many times? 5 6 is 30. Okay, remainder will be 1. So 1 means 12. So we can say 5 2s are, again 2 will be remainder, it is 5 5s are. Again this I am writing as 5 125 times. And this I am writing as 25 times. And this I am writing as 5 5s are. Okay. Children, these 3, 1, 2, 5, I can write as 5 5 5 5. How many times 5 is repeating children here? Just count it. 1 2 3 4 5. So this I am writing as 2 to the power of 0 and 5 to the power of 5. Okay. 2 to the power of 0 and 5 to the power of 5. See, if you are able to write denominator, if you are able to write 2 to the power of n and 5 to the power of m. So what did I say? It is a terminating decimal expansion. If you are not able to write this form, then it is what? A non-terminating repeating decimal expansion. So look at the denominator children here. This 3125 I am writing 2 power 0 and 5 to the power of 5. So I can say this is a terminating decimal expansion. Because it is following what? It is satisfying our condition. So I can say it is terminating decimal expansion. Clear, children? This example question, it's a very easy, children. Okay.